In this video, we're talking about setting up MPLS, or multi-protocol label switching. What MPLS is it's basically one more way that we can connect sites together across a WAN or provider's set of equipment. Now, we've looked at different ways to do this. Site-to-site VPN being one of the more costly in terms of bandwidth, but maybe the easiest or most preferred way. We've looked at ATM, which is using plain old telephone stuff, frame relay, which is serial. We've looked at Ethernet, PPP, which is serial, or we could do PPP over Ethernet, having leased lines and all their pros and cons. But MPLS is just one more way to link our remote sites together. Now, MPLS was originally developed by Cisco, but because of some of the benefits and speed of it, it was pretty quickly adopted and standardized throughout the industry. There's still a lot of places running MPLS today, which is another reason that we wanted to take a look at it. Now, MPLS is a little bit different than your standard Layer 3 forwarding paradigm. In Layer 3 forwarding, when a packet reaches a router, the router's going to take a look at the network layer details of that packet and make a decision based upon what it finds. So it's going to look at things like the time to live, the source and destination addresses. It passes that on to see if that traffic should be allowed or denied. And it also has to look up in the routing table to see where the best path for that to go is. So layer 3, although we're very familiar and very common with it, is not necessarily the most efficient. What's really cool to look at is when you see something like MPLS. When MPLS sees a packet, only one router participating in an MPLS cloud or a group of MPLS routers needs to analyze that network layer detail. After that, the ingress router, or the first one to receive a packet that's untagged or unnoticed so far, identifies it and adds on a stream label or a tag. Basically what those are is 20-bit numbers that are going to identify the packet, much like what you saw with frame relay or even VLANs as well. When you see a tag or a label, we're talking about basically the same thing with that, so we're going to use those words interchangeably. But again, the idea is that when a packet enters a network, we're going to label it, and all of the routing or decisions based on where that packet should go happen just strictly at the tag, which sits at the layer 2, or the Ethernet frame. What we call this is label forwarding instance-based routing. The process works the same as an IP routing table would. It's just quicker. We can deal with the packets at a lower level and move them throughout our network with a little bit less overhead as well. It also helps us provide a method of traffic separation. We're going to see that with some virtual routing instances and things like that that our providers do. Now, MPLS still relies on standard routing protocols like OSPF and EIGRP. We have to learn about the remote networks somehow, but once we know about those networks, we don't need to rely on those quite as heavily. BGP is able to actually handle the tags on its own as well, and it's a really cool, really efficient way of doing things, but we have to look at it from an external or maybe an internal perspective as to what protocols we're going to use. So the label descriptions, basically like I said before, they're a 20-bit number. It's an unsigned integer, meaning it can go from 0 through 1,048,575. Those numbers don't really mean as much to us because more often than not, we're going to set up some version of dynamic MPLS rather than statically assigning tags to each packet and then mapping those to their destinations. You should know that there's some ranges that we can and cannot use if we were going to do static mappings, and our routers even will pick ranges dynamically based within those allowed ones as well. So for instance, if you tried to label a packet with 0 through 15, there's reservations on those numbers to signify a packet is either untagged, maybe the label should be changed. It means different things to MPLS, so we can't just start picking and choosing random numbers. If you were going to statically assign these labels, you'd want to live in that very bottom bullet point there, the 100,000 through 1,048,575. Fortunately, most of our protocols that will do this for us, so we don't have to worry about it. Now, MPLS is sometimes referred to as a layer 2.5 technology, meaning it sits between layers 2 and 3 of the OSI model. In layer 2, where we dealt purely with Ethernet frames, we had things like ATM, frame relay, Ethernet, Cisco's HDLC, and GRE tunnels. And in layer 3, we had IPs and IPv6. The reason this is called a layer 2.5 protocol is that it adds a tag at layer 2, but the ingress router still needs to process the layer 3 or that network layer data to make its first forwarding decision. So it kind of sits between those two levels in the OSI, but it's really kind of neat how all of this works here. What we have is, you see a standard packet here at the bottom. So the blue layer 2 header typically is butted right up to the IP packet in kind of that green color. But what MPLS does is it adds a section right in the middle to include that 20-bit label. Where you see EXP, that's another abbreviation, same thing as COS or class of service. It's how we identify what type of a packet we're dealing with, and we can make decisions to what resources that packet will get, like how much bandwidth, what its priority is, things like that. The S is the bottom of the stack, so we can actually have more than one label per packet. We'll talk about that next, and a standard TTL. Now, one thing that we didn't talk about is how these routers learn about labels from each other. One way we could do that was, again, statically setting up the labels that our neighbor routers know about and then mapping those back and forth. Or we can use things called LDP, which is the Label Discovery Protocol. And that's something that we're going to use when we actually go configure this as well. Now, an MPLS router is also called a label switch router because of obviously what it's doing is dealing with labels on an Ethernet frame and figuring out where those packets should go. Now, I said before that the labels operate on somewhat of a stack. If you've done anything with assembly or sort of know how a computer's memory works, if you're programmatically looking at it, the labels operate in a very similar stack solution. So our routers have three main jobs dealing with labels. Number one, they can push a label, meaning they're going to add a label to a packet. They can pop a label, meaning they're going to remove a label from a packet. Or they can swap labels, meaning they're going to take a label off and put a new one back on, so they're kind of changing where that packet should go next. And much like the stack, the first label that gets pushed on will be at the very bottom of the stack. Every other label we push on kind of grows that stack. When we try to pop those labels, we have to pop the last one that was added. So in this case, if you look at the picture on the right, MPLS 1 would be at the bottom of the stack, MPLS 3 would be at the top of the stack. If a router is going to pop a label, meaning, hey, I saw this label, made a decision, we don't need it anymore, it would have to pop label 3. So it's the newest label that was added onto it. From a functional, purely can we implement this thing standpoint, you don't need to know so much about the inner workings of that, but I thought it was really interesting how it's dealing with all of these different labels as it traverses the network. And within the LSRs, there's really three types that we have. We have an ingress router, which sits at the edge of your provider edge, rather. So PE is provider edge. Basically what it's doing is it's receiving packets coming in and it's putting the first tag on them. So your customer would send something to the MPLS edge or that provider edge. The ingress router would add the first tag to it. Egress routers sit at the very opposite end. They're the last router of the provider network, and they remove the tags before sending that packet out to the other customer end. We have intermediate or transit routers, basically anybody that sits in between. They're going to be pushing, popping, and swapping labels, and we get something that looks like this. So if we're moving from left to right, the very left router sitting at the edge of the network would be the provider edge, and that's the ingress router. When it receives an IP packet, it looks at the network layer information, classifies it into a forwarding equivalent class, and adds a label to it. As it moves down the line, the intermediate routers really only care about the label, not what was in that layer 3 header. So they're going to do swapping between the ingress and the egress, so keep trying to get that closer to the egress router. When the egress router sees that very last labeled packet, it's going to do a pop operation, get us back to a normal IP packet, and it can send that back out to the other customer edge. This whole diagram, so the whole path a packet takes through this network, is called a label switched path, or an LSP. Like I said before, there's different ways we can do this. We can set them all up statically. We don't need any additional protocols. Just like with a static route, it's very low overhead, it's quick to process, but we can't really change it or adapt it or do anything easily that way. With LDP, which is dynamic basically, or the label distribution protocol, our routers are going to talk to our neighbors and they're going to figure out what labels that they know about and exchange that information amongst each other. RSVP works pretty much the same way, just using a little bit different protocol set. It doesn't matter which LSP model you choose. The goal is to provide end-to-end connectivity. And we can do some kind of cool stuff on top of that, like doing layer 2 and layer 3 VPNs. We can do class of service or quality of service, which is sometimes referred to as traffic engineering. Now, I don't know that we're going to go configure these things, but I wanted you to at least be aware of them if you wanted to go kind of take this the next step further. Layer 2 VPNs, so dealing only with the Ethernet frames, are called overlay VPNs. Layer 3 VPNs, like we've seen before, on our site-to-site or peer-to-peer VPNs, traditional IP-based VPNs. So we know quite a bit about those at this point, so we'll kind of skip over that. Quality of service, like I said before, we can actually tag the packets with a classification or that COS, and based on that COS value, we can assign network resources to those packets. We can choose who gets top priority to the network, who's maybe a little bit less important and it can handle some delay, and we can start to classify those things down a little bit more too. Basically, once we figure out what quality of service we should be using, that traffic gets inserted into a TE or traffic engineering tunnel, and then that path gets created based off of that. Now, we were going to look at static LSP, but I've opted to just do LDP. But basically with static LSP, we have to identify a router as the ingress, we have to identify our intermediate and transit routers, as well as the egress router. Once we get past that, you can kind of see in this type of configuration for a Juniper, we would have to go set those static labels up, identify the router as ingress or egress, specify the next hops, specify the remote, the farthest destination network we're trying to get to, and tell that router to push or pop a label on it. In this case, we had an ingress router pushing label 1000123 onto those packets. What we would see next, if we looked at the edge router, is that any packet tagged with that 1000123, it would push that to the next hop of 13.3.3.3 and then pop the label. As you can probably see, syntactically this isn't too complex, but when you get a larger network, you're having to manage the pushes and pops and keep track of all these labels and where they should go, it really doesn't scale well. What we're going to do is set up LDP, signaled LSPs, basically meaning instead of statically doing it, why not just let those routers figure this out for us? On the SRXs, we have to disable the security services from the device, meaning we're going to transform it from a flow-based device into a packet-based inspection system. We have to enable MPLS, which will force us to commit and then reboot. After that, we set up our network interfaces, so just IP addresses, our interior gateway protocol like OSPF, and then we go set up LDP on both the routers. After that, I'll show you some commands to verify and make sure that this thing is working, but it shouldn't be too bad once we get past those few steps. So that's all I've got for you in this one. Just wanted to give you an introduction to MPLS, and we can go on from there.